Last time on History Bites for Education.
Tensions with the Soviets were high, and we knew missiles could reach U.S. soil in minutes.
Before this decade is out, of landing a man on the moon and returning him safely to the Earth.
However, most people eventually settled on a design for a massive semi-powered catapult.
March 23, 1983, President Ronald Reagan announces the beginning of a new strategic defense initiative, a missile defense system which would protect the United States from ballistic attack. The SDIO was an organization within the U.S. Department of Defense. The plan was to develop advanced weapons and create an array of ground and space-based systems which could identify and intercept missile attacks.
We plan to develop lasers and particle beam weapons, in addition to advanced supercomputers that could track missiles and coordinate a counteroffensive.
On March 24th, just one day after Reagan's speech, the Washington Post released an article quoting Democratic Senator Ted Kennedy. He described the program as a reckless Star Wars scheme, a nickname which would stick for the remainder of the operation.
The space defense of the SDIO was arguably the most important part. It would allow the United States to rapidly and automatically detect when Soviets launched intercontinental ballistic missiles, and then send heat-seeking missiles of our own to intercept them.
The most practical plan for a space-based program came from Lowell Wood at the Lawrence Livermore National Laboratory in California. Along with Edward Teller, Wood proposed the Brilliant Pebbles system, a network of 7,000 heat-seeking missiles orbiting the Earth.
Wood's Brilliant Pebbles plan was ingenious. Since so many missiles were orbiting constantly, it guaranteed that nearly 1,000 would always be over Soviet territory and ready to fire. However, there was one problem we ran into. At the time, NASA didn't have enough fuel to launch so many capsules into space. Unless we found an alternative source of propulsion, the project would be unsuccessful.
At the time of Lowell Wood's proposal, NASA estimated that they only had enough fuel supply to launch 2,000 of the required 7,000 missiles. To continue the mission, scientists would need to find an alternative method for lifting the missiles into orbit. Suddenly, on July 12, 1986, then NASA engineer Sandra Meyer made a shocking discovery while sorting through classified documents from older missions.
I was looking through past technology NASA had used to launch spacecraft when I stumbled upon a classified report from the early 70s. It was from a special mission called Project Kennedy, which appeared to be a plan to host the 1972 Winter Olympic Games on Europa.
The documents Meyer found were in fact a summary report, created after Project Kennedy had been discontinued in 1971. The project was created in response to heightened conflict in the Cold War. In the event of full-scale nuclear war, the International Olympic Committee wanted a plan to ensure that the Winter Olympics could still be held. Under President Nixon, the IOC partnered with NASA to develop Project Kennedy, which would transport nearly 600 athletes and judges to Europa, where the Olympic Games could be held safely. However, due to peace efforts initiated by the Soviets, the plan was discontinued and the technologies developed were left classified for decades.
The part of the report which struck me was the detailed blueprint for the 250-meter trebuchet which was going to be constructed. It would be used to send 25 capsules on a rapid flight to Europa. This design was remarkable because it meant each capsule only needed minimal fuel for control later. All of the launch force was provided by the 300-ton weight on the trebuchet.
With the discovery of these documents, NASA finally had the necessary resources to begin Brilliant Pebbles. 7,000 missiles weighing a little over 2 kilograms each would be developed and loaded into the trebuchet. They would be deployed in groups of 250 for a total of 28 launches. After making this revolutionary discovery, Sandra Meyer brought the trebuchet design to Paul Wilkerson, who was the director of the Efficiency Propulsion Technological Research Group, also known as EPTR. This was the group tasked with developing technology to launch the Brilliant Pebbles system into space.
Once EPTR finalized the plans for the launch, we were able to begin construction. Under orders from President Reagan, we needed to have the trebuchet frame fully constructed by May of 1987.
Beginning in October of 1986, the SDIO began an intensive 6-month construction project for the trebuchet. Over 500 workers were hired and transported to the construction facility in Cape Canaveral, Florida. A fleet of cargo ships was assembled, bringing monthly deposits of steel and concrete. By the end of the operation, over 20,000 tons of material were delivered, totaling $3.4 billion US.
It's estimated that initial SDI plans would have cost the U.S. government over $50 billion, which is well over $100 billion in today's dollars. A significant portion of this money was dedicated to the space-based defense systems. Since space technology was still an emerging field, there was very little production going on, and costs were significantly higher than they would be today.
We managed to have the foundation of the trebuchet fully constructed by mid-January. One of the engineers on the team found a way to drastically cut down the concrete by using a few steel reinforcements, so we were able to keep the same support while saving over $500 million.
Construction of the trebuchet continued over the next 4 months, with the frame being completed by the end of March. Meanwhile, the massive 1,000-ton arm, which would hold the counterbalance and launch craft, was being built at a second site a quarter mile from the frame. In April, the arm was brought to the frame in 3 pieces on the crawler transporter, which NASA was using to move spacecraft at the time. Finally, on April 28, 1987, the trebuchet was fully assembled and the counterweight was in position for launch. Now, NASA scientists could begin to test launches with dummy missiles. At the same time, Brilliant Pebbles prototypes were being developed off-site at the Lawrence Livermore National Laboratory.
By the time the engineers in Florida had finished the trebuchet, we were on the 5th round of tests for Brilliant Pebbles. We made specialized sensors which could sit on them, including an infrared sensor that could detect Soviet ballistic missiles. And even with all the equipment on the pebbles themselves, one of the scientists found a way to substitute some of the metal for a lightweight synthetic plastic, which got the total weight down to just 1.8 kilograms each.
With many new improvements to the Brilliant Pebbles and the trebuchet fully constructed, launch of the Space-Based Strategic Defense Initiative was in sight. Lowell Wood, the head of the project, brought the latest prototype to Reagan in November of 1987.
We went to Reagan with a prototype of the Pebbles system and summary report for the mission. It had information like the total cost for production and deployment. I was brought along with Wood due to my experience with space travel, so I could review the Pebble design for launch. Our goal was to get Reagan to okay the operation, which would allow us to proceed to the manufacturing stage.
The report given to Reagan made a conservative cost estimate of $12 billion for the production and launch of all 7,000 missiles. Though Reagan was a vocal supporter of the SDI, he was unconvinced that Congress would authorize the Brilliant Pebbles system at such a high cost.
Congress during Reagan's second term in office had a strong Democratic majority. Reagan knew that with Cold War tensions easing, it would be difficult for him to secure funding for the Brilliant Pebbles system. However, he was still optimistic that if he could cut costs to under $10 billion, it might be possible that the project could continue.
Reagan did not want to reject Wood's proposal entirely, but he knew that there would need to be cuts in the budget. He sent Wood a letter detailing the requirements for manufacturing to begin.
Unfortunately, at the monetary estimate you provided in your report, I do not see any way for Brilliant Pebbles to continue. However, I believe that if gross costs can be cut to under $10 billion, Congress may be willing to approve the project.
When we got the response from Reagan saying that the project was rejected, we were all pretty surprised. We thought the cost had already been lowered enough that he would approve it immediately. However, no one wanted the setback to stop the project altogether. Wood assembled all the engineers, and we tried to come up with an idea for producing the pebbles more efficiently.
Under the existing proposal, each pebble would cost nearly $1.5 million to produce. However, Wood believed that there were inefficiencies in the pebbles which could be removed. The dimensions of the fuel storage tank had been adjusted only through trial and error, and he decided that by finding the optimal diameter to maintain the same fuel volume, they could drastically reduce the metal required. This could mean savings of up to $3 billion.
Wood saw that the current method of dividing the fuel tank into 2 equal cylinders was inefficient, so I was told to find a better shape. I conducted many trials with different possible options and recorded how they would perform in space and the amount of money it would cost to produce them.
The trials more conducted revealed that combining the fuel tanks and repositioning them at the front of the missile was more cost-effective. From there, he found a dome cylinder to be the most efficient, both for its speed due to aerodynamics and for its volume to surface ratio. Now, Wood's team needed to determine the precise dimensions of the storage tank to minimize the cost of each pebble. If volume could be maintained but the surface area decreased, less metal would be required, and the pebble would be much cheaper to produce.
Using calculus optimization techniques, scientists at NASA were able to find the ideal radius and height. They deduced 2 formulas for the surface area and volume of the dome cylindrical fuel tank. To maintain the same fuel capacity as the previous model, the volume had to be 19,750 cubic centimeters. The scientists needed to solve the volume equation for height in order to substitute when computing surface area. By subtracting 2/3 pi r cubed to isolate the term with h, and dividing by pi r squared, they found a formula relating radius to height. Now, returning to the surface area equation, the height can be substituted for the relationship derived from volume. Distributing the pi and r outside the parentheses allows pi and r to cancel in the denominator. The 2 can then be distributed into the numerator, yielding 39,500 cubic centimeters and 4/3 pi r cubed. Then, by separating the fraction into 2 terms, the r in the denominator brings the r cubed down to r squared. From here, like terms with r squared can combine to yield 5/3 pi r squared. Moving r to the numerator offers a negative exponent, which is useful later. With the S of r equation simplified, the maximum surface area must be determined. By using calculus, the derivative can be found and set equal to 0 to locate the critical points, which represent local minimums and maximums in the original surface area function. S prime of r is calculated using power rule. In the first term, the 2 in the exponent is multiplied by the coefficient and dropped to 1. In the second term, the -1 in the exponent makes the coefficient negative and drops the -2. Setting the derivative equal to 0 leaves -39,500 cubic centimeters times r to the -2 plus 10/3 pi r. From here, 10/3 r can be pulled from each term, leaving 11,850 cubic centimeters. Since the factors are multiplied and equal 0, each can be set equal to 0 to individually reveal both roots of the function, the critical points. 10/3 r simplifies to r equals 0. By subtracting pi, moving the r to the -3rd term to the other side, and dividing by 11,000, r can be isolated. Inverting both fractions to remove the negative exponent leaves r cubed equal to 11,850 cubic centimeters over pi. This simplifies to 3,700, and the cube root comes out to 15.567 centimeters. 0 is not a reasonable radius because such a tank would not hold any fuel. Thus, the only remaining critical point is at r equals 15.567 centimeters. If this is plugged into the formula for height and simplified, the dimensions of the dome cylinder fuel tank are found to be radius 15.567 by height 15.564 in centimeters. Plugging the radius and height into the original surface equation shows that the fuel tank has a surface area of 3,806.2 square centimeters, which uses less material and is significantly cheaper to produce for Wood's team.
Once the Pebble prototype had been updated with the new fuel tank, cost estimates decreased massively. Instead of costing $1.5 million per Pebble, the new design was only $1.3 million.
Reagan was ecstatic when he saw the new price estimates. He immediately authorized us to start producing them, and kept asking lots of questions about how long it would take before they were deployed. It was pretty amazing how different he acted once the cost had dropped.
After a meeting with NASA executives, August of 1989 was chosen as the launch date for the first round of Brilliant Pebbles. That gave NASA 18 months to produce 7,000 pebbles and transport them to the Trebuchet launch site.
Finally, after years of research and development, it looked like Brilliant Pebbles might actually be deployed. However, it still wasn't certain that the Strategic Defense Initiative would actually be needed. Since the Cold War seemed to be coming to an end, Congress was starting to question the need for such a massive defense program.
Unfortunately for Wood and the Brilliant Pebbles team, it was becoming increasingly likely that the project would be cancelled despite its recent approval by Reagan. By July of 1988, 500 pebbles were already produced, but Congress was becoming hostile toward the program. With the election cycle nearing, many politicians were eager to initiate budget cuts and reduce tax burdens in the hope of re-election.
The threat of Brilliant Pebbles being cancelled was significant, but under Reagan we were confident that it would still proceed. However, as his second term neared its end, there was a lot of talk about the project being discontinued.
After Reagan's farewell speech on January 11th, it was obvious that Brilliant Pebbles would soon be cancelled. Immediately after the inauguration of George H.W. Bush, he announced his plans to cut back on certain defense programs with the Strategic Defense Initiative, including Brilliant Pebbles. By April of 1989, the project was formally terminated with an executive order from President Bush.
Due to the increasing threat of offensive from the Soviet Union, the Brilliant Pebbles project, a section of the Strategic Defense Initiative organization, is hereby canceled. This is effective immediately, April 18, 1989.
Suddenly, the threat of discontinuation became reality for the Brilliant Pebbles team. Wood's master plan for a space-based defense system was cancelled, and the 4,000 missiles already produced became immediately obsolete.
After the project was canceled, we spent months dismantling the pebbles that had been produced. It also took a while to dismantle the massive trebuchet for launching them, which was eventually reused for metal and other spacecraft.
Finally, in November of 1989, Project Brilliant Pebbles was entirely discontinued, with the trebuchet fully dismantled and all 4,000 pebbles recycled. There was almost no trace of the project remaining. Soon after, Clinton's presidency marked the official end of the Strategic Defense Initiative as a whole. With few projects ever completed and the threat of nuclear war over, the massive program Reagan devised was no longer necessary. The SDIO, along with the Brilliant Pebbles and the rest of the space-based defense, was finished, a forgotten detail of the frantic struggle with the Soviet Union.
Next time on History Bites for Education.
We found that Desmos was a tool that was extremely effective for modeling that relationship.
After being officially authorized by the president, the mission was codenamed Project Schwoe.
Lead investigators suspected that the Illuminati could be involved, but evidence pointed to a high school calculus teacher from Michigan.